We'll just start. Yeah, okay. Are you able to see my screen?
Yes, ma'am.
Yeah, okay. So today let us just discuss about roughly about, not like we don't have much in our syllabus also, but we'll just mention about imbalanced data. I think few of you are having it in your data set also, and maybe when you have your minor project, maybe there also later when you do machine learning projects, you might have this issue. So at least you should be familiar that what is it and when, like what kind of things you do there. Okay, and then we have something called ensemble methods. So we'll just see that also. Okay. So I think when we discussed about the metrics, how we evaluate our models, we had discussed about class imbalance problem. Okay. If I'm right, I think when we had accuracy as a measure, we told accuracy is not the best because when we have a class imbalance issue, we might have we might have an issue. So if you just depend on accuracy. So what is this class imbalance data set? So first of all, class, we have mentioned it as class. So of course, it's a supervised classification problem. Assuming, let us say, example of binary class. So say, for example, if I have a data set of, say, 4,000 data of, say, some patients, maybe details of cancer. Okay. So maybe I have 4,000 patient details, out of which I may have only, say, 100 patients with cancers, isn't it? So like we don't have like lot of patients with cancer. We may have only few. So we may have only very less number of instances for that class where the patient is having cancer, but the class the patient does not have cancer may have, say, remaining like 3,990 data. Okay, so then there is a large imbalance in this data set. So usually in medical diagnosis, you may have this. Or say, for example, you have fraud detection. So there are normal connections out of which, or some normal actions out of which very few would be fraudulent transactions or connections, etc. Or say some network connections and there is an attack. Very few could be like if you're collecting data of like so many days, etc. You might get only very few data where there was an attack or something. So then we say it is a class imbalance problem. So in the slide it is put positive, negative. Don't bother like that. There is nothing like positive, negative, etc. One class is very rare and the other class would have large number of samples. So there is an imbalance in the class. Okay, so that is our class imbalance problem. Okay, if you see, like say for example, so what is the class imbalance problem? So total number of one class would be um, far less than the total number of data in the other class. So it can be even in the multi-class classification problems also. Like say if you have 4 classes, maybe one kind of disease is very, very less. Okay, and the others, like say for example, if you take general, say flu, it is very frequent, and say maybe some other kind of like very usual kind of diseases versus like very rare kind of disease. So if that is one kind of category you are looking, it might have very less number of samples in it. So then also we say it is class imbalance problem. Okay, so usually when you have one class with very less number of data and the others being large. So that is our class imbalance problem. So why is it a problem? First of all, we have already seen accuracy measures or the measures what we use always need not give, actually they give equal weightage for all classes. Like we just see sometimes when we say accuracy, we just say the total number of correct predictions. So what happens, like say in the previous example when I mentioned, so I said only 10 samples with cancer and all other samples of the patients in that 4,000 data are without cancer. So when my intention is to predict the cancer or something like that. So maybe let us assume it's 100. Okay. So even then it is a imbalance. So, so when we say that, so for example, if you have only 100 samples where the patient has cancer, and when we try predicting it, your model, of course, will learn more. We have more data for the class with patients not having cancer. So even these 100 might be misclassified as patient not having cancer. And what happens is when you take accuracy as a measure, we may not even identify because we have large number of samples which are correctly classified as not cancerous and very less data which is misclassified. So we feel that, okay, it is only very less. But then since there is an imbalance, we did not understand the number of samples in that class is less. That is why we feel it is very less number of misclassification. So that where there we discussed. So why accuracy is not a proper measure, etc. So usually your algorithms work best when we have not equal, but at least so equal means it is like 50-50. So at least kind of say 70-30 or 60-40 kind of sample should be there in one class and the other class. You cannot have like one class is very less, like 10%, and then we have more in the other class, more number of data in other class. Then it is class imbalance problem. Okay. So that is our class imbalance problem. So how do we overcome that? Okay, the major like the basic approaches now too we have lot of advanced techniques etc for handling these, but the very basic approaches were like the basic initial approaches were sampling methods. So either oversampling or undersampling. So oversampling, from the term we can, so usually when we say as considering my previous example of 4,000 data of patients, out of which 100 are having cancer, that belongs to one class, and the remaining 3,900 belongs to another class. So the class where I told I have only 100, very less number of samples, we say it as minority class. So the patient, the cancer, yes, cancer equal to yes is the class which I tell in this example as minority class, and the other class would be majority class. So if it is oversampling technique is what you're going to use to handle this imbalanced data, what you would do is the number of samples in the minority class you try to increase. Okay, so that you don't have major issues with majority samples taking up your model and then just learning that alone, your model learning only the majority class. That issue may not be there because you're increasing your minority class. Okay, and undersampling is actually removing some of the majority class, some in the sense some instances from the majority class. But this is possible only if you have enough data set. Like if your data is very huge and then you see there is an imbalance, of course you can remove some from the majority class and make it like approximately equal. So that is another technique. Undersampling you can use only if you have enough data to deal with. Otherwise it may not work. Okay, so when you have this oversampling and undersampling, there are some variations how you do it, etc. Okay, so this is just randomly eliminate from the tuples, that is undersampling. Oversampling can be some basic approach could be when I say there is a imbalance, we can say oversampling means we are just duplicating some more data, but that is a very naive approach. So there are certain algorithms, okay, like something called SMOT. It is actually synthetically generating some samples. Okay, so let us see what it is. I mean, we are not talking about the algorithm, etc., but we'll just mention what it is. So now when I say about imbalanced data, if you can see my figure, the first figure is the imbalanced data. You can see a lot of blue points, the class belonging, so one class, and the minority class, you can see very few data points. which is having red color. So that is another class. Okay, so that is imbalanced data. So you understand that you have an imbalanced data. Now, how do we solve it? It can be undersampling or oversampling. Now, what is undersampling? You reduce the samples in the majority class. Your majority class was represented using blue color. So that is now reduced, if you can see, after undersampling. Whereas oversampling, we increase the number of minority class. Our minority class was represented as red. So now it is increased. So that is why there is a difference. Okay. So this is actually oversampling and undersampling. You don't have to learn like SMOT, etc. is not part of your syllabus. Like if you're interested, of course, you will get the paper which talks about the SMOT. So I don't remember what is that expansion synthetical majority oversampling something, I guess. So SMOT, what it does is it does not duplicate. It actually synthetically generates some samples, okay, and which are close to the minority samples, like the distance wise, etc. So it is not, I'm just telling like very basic this thing. Of course, the algorithm base meaning is this way. So it actually generates some samples. So if you can see the figure, the square ones are the majority class samples. The black circles are our minority class samples. And then we have some synthetic samples which are generated by SMOT, which is very close to the minority samples. So we try to, I mean, the SMOT tries to generate some synthetic samples, instances. Okay, when we say samples, since we are drawing it on the two-dimensional this thing, don't think like that. When we say you're generating or synthesizing a new sample, it is your instance. If you had say 24 features, we are actually generating a new sample with all these 24 features that way. Okay, so which are close to the minority samples. Okay, so this is one approach. SMOT itself has a lot of variations, etc., but that is out of scope. But in this particular this thing, but understand that you have oversampling techniques where SMOT is one basic approach which actually worked well. And of course, say if you're working with say medical data, etc. Okay, so when you have real data, when you synthesize some data, whether it is sensible, etc., you might have that kind of a doubt. So of course, when we in actuality, you may have this issue of imbalance in the data, because you don't get like very clean data. Of course, if you think about say fraud detection, or say network intrusion, or applications like detection of some disease, you understand that of course there would be an imbalance in the data, because when you consider patients with cancer, if I have 4,000 patient details, it is very known fact that all the 4,000 will not have, even 2,000 will not have cancer, because it is not so frequently occurring disease. So we may have some 100 people who had cancer, the rest who may not have. So of course it will, the actual data would be, we cannot have like say 1 lakh data of the patient also. We might have only maybe 4,000. So the real data might have such issues. So we have to somehow come up with certain techniques which can handle this. So that is why oversampling techniques like SMOOT has come up, where it is synthesizing some instances which are close to the minority samples, and then we move on to the machine learning algorithm. So it will be performing better once you do this oversampling. So usually when like say for example, if you have a imbalanced data set, and say you're going to perform a classification algorithm, what the kind of analysis you do is you try to simply apply an algorithm and see what kind of results it gives. Then you try some oversampling techniques, and then you see what is the responding, not accuracy, but all the measures, like the model, how it is performed. So this is what we have to talk about our class imbalance. Any doubt here? Am I audible?
Yes, ma'am.
Okay,
No doubt.
okay. Yeah, yeah. Okay. So So this is about our class imbalance. So it's actually, since it is, I am just taking this week 2 classes, and then again, ma'am would be continuing the topic. So I thought I'll not bring in a new algorithm here. And anyway, coincidentally, Vikas also told that you have placements going on. So that is the reason why I thought I'll explain about this class imbalance now, and also the ensemble methods, which are not like a specific algorithm. It is all combination of models and things like that. So have you heard of this ensemble techniques? Okay, so let us see what it is. It is actually, of course, increasing the accuracy means increasing the performance is what it is meant. So it is usually, when we say ensemble, it is usually combination of models. Okay, we are trying to have different models on that data and then try to combine the prediction what it is giving, etc. Okay, so the popular ensemble methods are bagging and boosting. So let us see an ensemble. It is written ensemble also. We'll see that. So let us see what is bagging. Okay. So when we say bagging, so there is an analogy. So let me say for example, say one of your friend is having, he is not feeling well, and then you have taken him to a hospital, and then they say there is a immediate requirement of a surgery. So immediately you will not decide that, okay, we'll do a surgery, okay, unless it is very critical, like you don't have an option. What you would do is, just because like say emergency, you've just gone to some hospital where you don't know the doctors. So you just take the, I mean, when they say we need to have a surgery sometime this month soon, like we cannot we should be having. So what you would do is, of course, you will go to, you will contact other doctors in your family or in your connections, and then you will check with multiple doctors. Maybe you will go to another expert, I mean, special hospital where you can have other facilities, and then check with the doctors. So you will take multiple opinions, multiple doctors' opinion, isn't it? So now, say for example, I have taken 10 doctors' opinion. So most of the doctors told that surgery is not required. So usually what we generally do, okay, most of them told it is not required. So maybe we'll not proceed with surgery now. Maybe we'll have it later. Something of that sort is the conclusion what we make, isn't it? So similarly, if they, most of them told me that surgery might be required, it is very critical, I might go with it. So this is how we usually do. This is the same thing in our bagging. Okay, so just because I told this analogy, please don't write this in exam when I ask bagging. This is just an analogy for you to remember. When you tell what is bagging, you have to tell in respect to, with respect to your classifiers. So now what happens in our bagging? We have different, so say for example, we have a data set D. Okay, so we are taking certain tuples or instances each iteration, and it is sampling with replacement. Okay, so do you understand what is sampling with replacement? Say for example, just to tell what is sampling with replacement, I know you are very much aware of what it is. Anyway, we'll just tell what it is. So say for example, I have a bowl of, say, unique numbers from 0 to 9. Okay, so I am asked, so we are just picking a random sample of numbers from the bowl. So after I pick a number, if I keep it back, there are two options. I can keep it back or I can keep it aside. So if I keep it back, then next time when I pick, it can be selected again. So there is chance that it will be again selected. But if I put it aside, of course, it will be selected only once, isn't it? So when I say a population element, when I take it for some testing or for some training or some step, when I take from a population a sample, and if it is selected more than one, that means it is replay. I mean, what is that? We are sampling with replacement. So which means we are putting it back. So then we say it as sampling with replacement. And if you keep it aside and don't put it back, so which means it is without replacement. So that is what we talk about, sampling with replacement. So here in this bagging, when we talk for the training, it is sampling with replacement. So there are chances that some samples never get selected, Also, there are chances that some samples are selected multiple times. All that might happen. Now, what happens? So this is how you will select the tuples or instances, okay? So when I have D instances at each iteration I, the training set DI, okay? So that many samples. Say, for example, I have 1,000 data. At each iteration, I take, say, 100 samples, okay? 100 instances. Now what happens? The tuples are selected, and then there is a model for which the learning happens. Okay, so for D1, so the data set is split into, say, first time I pick 100 and then I say it is D1, and then a model is given, like, say, naive Bayes or decision tree or any algorithm. So I give, and then I try to predict. Now that is M1, we can say. Similarly, I repeat for different data parts which I have selected. So I'll again take 100. So maybe some are already selected ones, some are new ones, all that could happen. Now, so in the next iteration, again, I say that data set name is D2 from the same set of data, actual data, and then the model corresponding to it. So when I say model, now it doesn't mean that, so first iteration I have chosen SVM, second iteration I choose logistic regression, not that way. So if I say it is decision tree, it might be decision tree itself, but we are using different set of data and asking it to predict. So not predict, just learn. Okay, so the model 1 is learned, model 2 is learned. So like that, say if I do it 10 iterations, I have 10 different models. Now, when a new instance come for us to predict, so unknown instance come where we have to label. So what happens is we are asking these 10 of the models to predict. Now say if we have class 1 and say yes or no, if 6 of them predict it as say yes, we take it as yes. If majority is predicting it as no, we take it as no. So that is why we are telling the analogy of these doctors, multiple doctors, majority vote. So what happens? When you have an unknown sample, each classifier MI returns its class prediction. Then the bagged classifier, that is, altogether we count the votes, and we, in the sense, the algorithm counts the votes. It calculates the majority, and then that is the label assigned to it. Okay, so if it is prediction, if it is classification, this way. If it is prediction, we might, it might take the average value of each prediction for a given test tuple. Okay, so now of course, than predicting by just one classifier and getting a data, this would be more accurate and more robust. Okay, so there will be an accuracy increase in the prediction. So boost, this is bagging technique. These ensemble techniques usually we take to improve our model performance. We try when we are not getting good accuracy, etc. So this is bagging. Is it clear? Bagging is clear? Okay. Anyway, I'll repeat it again tomorrow. I'm just covering it. So boosting, sorry. So boosting is like, if I tell the analogy, so we told when we have, say, same situation, and say one of your friends is admitted in a hospital, and they ask you to go for a surgery. So you go and check with 10 doctors, and then 10 doctors have given their opinion. But then it is not like all the doctors you consider equally. You know that 5 of them are some specialist, senior specialist in that area. So you might give more weightage for some of them. Some of them may not have much weightage. Like you just know that they've just finished medicine and then just casually ask. So there are different weightages for the different doctors' opinion. So we take more weightage for those who are like experts in that field. So for them, we take more weightage, and then based on that weighted, now it is not simply majority, it is, there is a weight also associated. Some classifiers will be given more weightage when they are predicting. So by that way, altogether we get a weighted kind of a prediction. This is called boosting. Okay, so that difference, did you understand? There it was like equal weightage for everyone's prediction, and we just take the majority. Here it is majority, but then each classifier's prediction might have a different weightage. So we'll see one algorithm called Adabos. Then you will have more clarity on why this weightage, like how we'll give, etc. So there is something like you will have more attention to the instances misclassified by the model. That is also there. And also the each classifiers also will be given some weightage. We'll see we'll just discuss what is this Adabos in the next class. So then I think it will be more clear. But basic difference between what is this bagging and boosting, is it clear? You want me to repeat? Yes or no?
No, ma'am, understood.
Yeah, okay. So maybe I'll stop with this. I don't want to cover the algorithm because many of them are not there. So maybe next class we'll see that. Again, I'll just browse through all this again once more in case somebody wants to. That's all. So maybe you can prepare for your quiz. Tomorrow is